Hello there. Welcome again to our today's science lesson. The topic for today being evidence for chemical changes. You remember that in our previous lesson, we talked so much about chemical changes and physical changes, at least to show or to understand, to analyze the differences between a chemical change and a physical change. And in all those cases we saw, at least we had to see what makes a change to be called a physical change, or what makes a particular change to be called a chemical change. To go over the same, we have now to go deep into particularly seeing what really makes a chemical change to be called a change, a chemical change, and also what can you see on the surface physically that can easily tell you that a chemical change has taken place. And that gives us the topic for today. So in our previous case, just picking on one of the examples that will develop a basis for our today's topic, we majorly looked at rusting as a process where we saw that a metal can rust, particularly iron metal, and it rusts because the conditions necessary for rusting are prevailing, and that was the metal itself, oxygen gas, and water. But how would you tell that that metal has undergone rust? We said the color change on the surface of the metal will automatically show you whether the metal has undergone rusting or not, and that is being brown in color. It will show you that the metal has undergone rusting. So this gives us a basis that we can easily use physical appearance, physical processes, physical changes of materials to determine or to show you that a chemical change has taken place, but not just essentially to show you that a physical change has taken place. So physical changes can show you both physical and chemical changes, but for now we want to measure on chemical changes, but still utilize the physical changes of whatever process that is going on to show us a chemical change has taken place. So these are the common observations one can make physically to show that a chemical change has taken place. One is change in color. Change in color. Change in color of a substance. Change in color during a certain process can easily show you that a chemical change has taken place. An example here, we have seen rust as a very good example, whereby original iron metal is usually gray in color, but after rusting, it changes color to red brown, or sometimes just call it brown, which is because of the iron 3 ions present in the rust. The rust being called hydrated iron 3 oxide. So here we are using color change to show us that a change has taken place. Another example where color change is a sign or an aspect you can use to show that color change has taken place, a chemical reaction has taken place, is during a reaction or process like precipitation. In precipitation reaction, and we need first of all to understand what is precipitation before we proceed. In precipitation reactions, where a precipitate is a substance that is in solid form, but is formed from two reagents that are in solution form. So we are seeing a solution plus a solution giving us a solid. It will also form other products. That product can be in solution form, gas, or liquid form, but the most important part is the solid part that will have been formed. This solid part that has been formed from two solutions is what we call a precipitate. In short, we write it as PPT. We call it a precipitate. A good example is, for example, if you have lead to nitrate, that is lead nitrate, reacting with the potassium iodide. Potassium iodide. This is a colorless solution. This one is colorless. And this one is also colorless. But when you add these two, how will you know that a chemical reaction has taken place? How would you tell that a chemical reaction has taken place? Color change plays an important role here. And what will be the color change? You will find that the product that will be formed, which will be in solid form, the product formed which is in solid form will be yellow in color. Yellow in color. So the precipitate formed will be yellow in color. By using the yellow color, which is a precipitate, you will automatically confirm that the reaction you wanted has taken place, and which is a precipitation reaction. And that is by chemical formula. We have lead nitrate reacting with the potassium iodide, giving us lead iodide, which is solid and yellow in color. Solid and yellow in color. The other product that will be formed, I said there are other things you can form there depending on which reagents you are using. And in our case here, the other product that will be formed will be potassium nitrate. It will be potassium nitrate, which is colorless. And this one is a solution, AQ. That is a solution, but a solution that is colorless. So you will clearly see the yellow precipitate, which is potassium iodide. And some of these are usually reactions that you can easily use to confirm whether a particular reagent is what you thought it is or is not. For example, you go in a lab, a science lab, you get two colorless solutions. And somebody tells you one of the colorless solution is a lead-based solution or maybe an iodide-based solution. What will you do? Look for, using such information, you look for a solution now that you know. If it was a lead-based solution, but you're not so sure. But at least you can get a potassium iodide solution. You go prepare that solution. You can easily use that potassium iodide solution to test this other solution that is unknown by mixing the two, and in case you see a yellow precipitate, then it will have confirmed to you that for sure whatever you thought to be a lead solution, indeed it is a lead-based solution. What are you using? You are using color change to show that a chemical reaction has taken place. That is number one aspect we can use to identify chemical changes. Number two is change in temperature. Change in temperature. Change in temperature. Now this change in temperature is in two ways. There is change in temperature by increase in temperature, or change in temperature by reduction in temperature. So there is a increase in temperature, which is given by the sign negative. So I'm introducing here another aspect. As much as we are talking about change in temperature, there is a sign that you have to use to show that the reaction led to a change in temperature that is increase in temperature, or a change in temperature that is a reduction in temperature. So we have negative and positive, whereby when it is negative, it means the reaction is exothermic, and if it is positive, it is the endothermic. It is endothermic. What does exothermic or endothermic mean? And it has to do with also the sign. Exo means the system is losing energy. Exo means the system is losing energy. And here we are talking about heat energy. The system is losing heat energy. But when it loses, where does the lost energy go to? It goes to the environment. So the system is losing heat energy to the environment. So if this system is in a container like a beaker, you are in a science lab, there's a container we call a beaker. So you had two solutions or two reagents coming together, or maybe you are dissolving something. So I have, for example, concentrated sulfuric acid. I have concentrated sulfuric acid, and I add in water. Water is colorless. Concentrated sulfuric acid is colorless. The product shall form is colorless. So can I use change in color to show that a reaction has taken place? The answer is no. I cannot use that. I have to use something else. But this something else is now change in temperature. However, in the change in temperature, we have two aspects. Is it change in temperature negative or change in temperature positive? Change in temperature negative is called exothermic. And what does exothermic mean? Exothermic means the system here is now water and sulfuric acid combined. Concentrated sulfuric acid or concentrated sulfuric acid. 6 means I'm talking about the oxidation power of sulfur. In this acid is 6. So you can call it sulfuric 6 acid or sulfuric acid. That is 6 if you are interested in giving the oxidizing power of sulfur in the acid. But if you are not interested in that, then you can just comfortably call it a concentrated sulfuric acid. Now, since the system, which is water, being poured in concentrated acid, making it dilute, the system will either give out heat energy or absorb heat energy. For our case here, the system will give out heat energy. The system will give out heat energy. This heat energy given out will be felt by the environment. And the environment here is the beaker itself. This is the environment, and the air. So the beaker and the air is the environment. The beaker and the air here are the ones we are calling the environment. You as an individual, you will easily notice that there is change in temperature to the environment by you touching the beaker. If you touch the beaker, you will find the beaker is hot, and not just hot, very hot, that you will not be comfortable holding the beaker, meaning that there is a lot of heat energy that will be given out when this sulfuric acid is being diluted, what we call enthalpy change of solvation. Enthalpy change of solvation, so that's change in energy, is a topic on its own. We shall cover it later on, but it involves a change in energy which is being given out by the system. If you don't want to touch and know that there is heat energy that has been given out, then you can comfortably use a thermometer, which is also an apparatus that is used to check on physical change of heat energy. Physical change of heat energy. You can use a thermometer that will read before addition of water, maybe the temperature was 20.0 degrees centigrade, and on addition of water, the temperature can go as high as even 110, 20 degrees centigrade, because the temperature, the heat energy produces a lot of heat energy, raising the temperature to very high levels. So in such a case, we can call this reaction exothermic. Heat energy has been given out. And since it is a minus from the system, then it is given the sign negative. So the energy that will be given out is given the sign negative to show that heat energy was given out by the system. But we also have other cases where we have change in temperature, but the change in temperature is positive, what we can also call endothermic. What does this one mean? This means the system takes energy from the surrounding, from the environment. Here, the system was giving out energy to the environment, but endothermic, the system takes energy from the environment. So, if this container by the name a beaker was at a temperature of 23.5 degrees centigrade, then you pour in a reagent and add in another one. For example, here I'm having water. And I add there a solid to be dissolved by the name potassium nitrate. I add in potassium nitrate. That is to dissolve potassium nitrate in water. You will discover that by touching the container, on addition of potassium nitrate as you stir, you will find that the temperature as you felt previously, and at the end of the solid, which these are solid, dissolving, the beaker will be very cold. It will be cold. Why? Because as you are solvating these potassium nitrate, as you are dissolving potassium nitrate in water, enthalpy change of solvation, the system, which is now potassium nitrate solution, takes away heat energy from the environment, and that is from the beaker, that is from the air around, making now the beaker to be more cold than it was. So here, if it was 23.5, then it might go to maybe, let's say, 19.0 degrees centigrade, a lower temperature than the original, opposite of what we have just seen for dilution of sulfuric acid, enthalpy change of dilution, where we can assume this beaker was originally 23.5 degrees centigrade, and now it goes to a temperature of, let's say, 110 degrees centigrade. So this one was exothermic, but this is endothermic. Plus, it is a plus. The system is gaining heat energy from outside. So which means, in addition to what it had, it is getting from the environment. So it becomes a plus. So as you can see, that is our second aspect we can use to show that a reaction has taken place. A chemical reaction has taken place. Change in temperature, which is either positive, or that is an addition of temperature, heat energy, or a subtraction of temperature, which is because of the reduction in heat energy. Number 3 aspect we can use to show that a chemical reaction has taken place is production of sound. Sound production. Sound production. Remember, sound is a form of energy. Sound is a form of energy. So when you see a sound, we call it in science, when you observe sound. You cannot see sound, but you can observe sound. So when you observe sound being produced in a chemical, in a reaction, then it can easily tell you that that reaction is a chemical reaction, because for the sound to be produced, a change must have taken place. And if a change has taken place, then the change is automatically a chemical change. Let's look at an example. Let's use one of the most common. Maybe you are watching a movie, and in that movie they are using a grenade. In that movie, maybe they are using guns, a bullet. They are using a bomb. What do you get? A blast. Sound. So that sound shows that there is something that has taken place in that particular grenade, in that particular bomb, a reaction. Just like what we saw in TNT, that is trinitrotoluene. When that compound decomposes due to heat energy, remember, a grenade you have to ignite with a flame. So once that heat energy touches that point, it explodes. When it explodes, it means a chemical reaction has taken place inside. So what shows you that a chemical reaction has taken place? That sound that has been produced is a sure confirmation that a chemical reaction has taken place. Where else can you see a chemical reaction? Let's now go to our lab situation. You are in a science lab. You have been given a reagent like an acid. An acid. Then you have also been given a reaction like a carbonate. You have been given these two reagents. Let's give particular examples. An acid like hydrochloric acid, and it is reacting with a reagent which is a carbonate. An example is sodium carbonate. Hydrochloric acid and sodium carbonate. This is a colorless solution. This is a colorless solution. You may find that some of these reactions will not have substantial change in heat or temperature. Substantial change in temperature. So you cannot surely use change in temperature as a way. It will be there, but seeing it is not so perfect. So you cannot use change in temperature. Change in color is also not there. What are you going to use? Change in sound. That is, sound is produced. So you will find that in this reaction, you will form sodium chloride plus carbon 4 oxide or carbon dioxide plus water. So you are forming three things: sodium chloride, carbon dioxide, and water. This sodium chloride will be in a solution form. Water will be in a liquid form. The one that is totally different is carbon dioxide, which will be in a gas form. Now, being in a gas form, and it is being produced very fast. Being produced very fast. It goes out as it produces a sound, what we call a fizzing sound. Fizzing sound. Or you can say effervescence has taken place. Effervescence has taken place. So this effervescence is what produces a sound. That is what we call a fizzing sound. Like if you are opening something like a soda, you will also get such a sound. Why you get that sound is because in that soda, carbon dioxide has been used as a preservative. So as you open, it goes out. As it goes out, since it is going out very fast, it produces a sound, what you call a fizzing sound, and because of that sound, we can comfortably say a reaction has taken place. At least for soda, it is because it was being forced inside, now it is going out. But I'm talking about in a reaction where you didn't see a gas, but now a gas is being produced. A good example is what you have seen. This will confirm to you that surely a chemical reaction has taken place. Looking at the products, looking at the reagents, the two are not the same. Here we don't have water, there we have water. Here we don't have carbon dioxide, there we have it. Here we don't have sodium chloride, and there we have it, which are totally different from the reagents. This shows that a chemical reaction has taken place. Production of sound. Another aspect we can use to show that a reaction has taken place is number 4, change in volume. Change in volume. Change in volume. Here you have 2 or more reagents. You cannot use color change. You cannot use maybe change in temperature. And maybe furthermore, you cannot use sound production to confirm that a reaction has taken place. What else can you use? And number 4, we are seeing change in volume to be a very good aspect you will use to show that a reaction has taken place. Let's have an example here. You are in a lab. You have water in a beaker. Water in a beaker. And you have been told we have several colorless gases in the lab. We have several colorless gases in the lab. And one of the colorless gases is ammonia. Ammonia gas. We have ammonia gas as one of the gases in that lab. And you really need ammonium hydroxide solution to be used in a particular reaction. Like I will give a reaction where you will see a color change being involved and also change and maybe production of other things is being seen. So you will require ammonia and water. But how will you know that ammonia has now reacted with the water and whatever you wanted, which is ammonium hydroxide, has been formed? You just bubble the gas. We normally use a filter funnel. The filter funnel is used to increase the surface area of contact between the gas and the water into which the gas is dissolving. So inside we are having ammonia entering the water. This is a filter funnel. And the filter funnel, its purpose is there are 2 functions. One is to increase the surface area onto onto which the ammonia gas will be dissolving in this water. That's one, increase the surface area. Because assume this pipe was to go and get in touch with the water. Look at the surface here. It's so small. But with now the funnel, the surface is so wide. Because remember, the funnel is wide enough. So it comes in touch with the surface of water, comfortably increasing the surface and therefore making more ammonia gas to dissolve in water. Number 2 is to avoid sucking back of the solution that has been formed into the tube. Since ammonia is very soluble in water, ammonia is very soluble in water. After dissolving in the water, the point where it is coming from will appear or will be like a semi-vacuum. And maybe it is in a sensitive container. It's from a sensitive container. So when the gas has dissolved, water or this solution will easily be sucked back if the exit is narrow. If the exit is narrow, it will easily suck back the solution into the original container that was having ammonia. To avoid that, we use a funnel which will create a bigger surface that can not have enough. Remember, there are forces, two forces that make water to move up a tube or a pipe. If you have a pipe and it is dipped in water, for this water to move up here, you need two forces. We have what we call adhesive forces and cohesive forces. Adhesive forces are forces that make a particle or a substance get attached on the surface of a container. These are called adhesive forces. And we also have cohesive forces, that is the force that will make this particle want to attach to this one and also to this and this and this. So if you combine the two, they will make a liquid to move up a pipe. And that's why in a narrow one, a narrow pipe, there will be a lot of cohesive forces than in a wider pipe, making a narrow pipe to have a higher rise of a liquid in it than in a wider pipe. So the same applies here. When you have a narrow one, there will be faster addition of the molecules on the surface of the pipe, making it move back very fast. But in a wider one, the way the funnel is, the forces will be there, but will be very small to cause any problem. Now, that is to do with the adhesive and cohesive forces and the sucking back, which we have avoided, and we have also increased the surface area onto which ammonia is dissolving in water. But what are we going to see? Because of this gas, ammonia, dissolving very fast in water, the volume of this water will be seen rising very fast, until one may wonder, is there an injection of water from the bottom? And the answer is no. There is no injection of water from the bottom. What we are seeing is the rapid dissolving of ammonia in water. And in so doing, it makes water to create more air spaces between the water molecules, which are being occupied by the ammonia gas that is coming in as it dissolves. The dissolving ratio here is 1 to the ratio of 750. That's a very big ratio. A volume of water 1 to a volume of 750 of ammonia, which is very big. So this makes the volume of water, which is now coming out to be a solution, now not water, because as ammonia dissolves, it forms a solution, to rise in volume. By using that, it will have confirmed to you that surely there is a reaction that has taken place. Ammonia has dissolved in water, and now instead of having ammonia, you are now having ammonium hydroxide, which is a solution, but this one was a gas and this was a liquid, and this is the product, a chemical reaction. Look at it. Is this the same as this? No. And is this the same as this? Again, not. So it shows that there is a change in identity, change in name, change in mass, change in everything, confirming that this is a chemical reaction. But how did you see, or how did you know? Change in volume of the product in relation to the reagents. Another aspect we can use to show that a change has taken place a change has taken place is use of change in color, but not really color, but change in state. It may involve change in color, yes, but the main aspect here is change in state of the reagents in relation to the product. So change in state of products. Change in state of products. This is a similar case like what we saw in what we used in color change as the second example, where we saw potassium iodide and lead nitrate being used. As much as we used it to show change in color as an aspect you can use to show that a chemical change has taken place, but still we can use it as an example, plus another one to show that change in state of the products can also be used to show that a chemical change has taken place. May I start with the very first one, which was lead nitrate reacting with the potassium iodide, giving us lead iodide. Our point of interest is the lead iodide, which was a solid. We said that this is colorless, but this one is yellow. But it's not just yellow, it is a yellow solid. This is a solution, this is a solution, but this is a solid. So what are we seeing? Though we are also talking about color, but we can also talk about something else in addition. And the addition here is change in state, from liquid state to solid state. So by you forming a precipitate, which is a solid, it confirms to you that surely a chemical change has taken place. So this one is a yellow precipitate, yellow PPT. What else can we use? We have said change in state, number one. And number two, we can use a reaction of what we have learned in volume, which is ammonium hydroxide reacting with the copper, for example, copper nitrate. Copper nitrate. So we have our ammonium hydroxide that we have just formed in this part, which is colorless solution. And here we have copper nitrate. Now I'm using copper nitrate to show you that it's not a must that we always talk about colorless solution. We can also talk about colored solution. So this is a solution, but it is blue in color. So this is a solution, but it is blue in color. This one is colorless, a solution. Now when these two react, that's ammonium hydroxide and copper nitrate react, copper combines with the hydroxide to form copper hydroxide, copper 2 hydroxide. I'm mentioning 2 because copper has 2 oxidation numbers, that is copper 1 and copper 2. The common one we are talking about here is copper 2 hydroxide. The copper 2 hydroxide that has been formed is S, meaning that it is insoluble. It is insoluble. So what are we seeing? We are seeing a change in state: aqueous, that is a solution; liquid state, solid state. So change in state as a good example to show that a chemical reaction has taken place. However, it is also in addition to what? Change in color. So as you can see, it's not a must that you only use one aspect. You can use 2, 1, 3, or all of them, because we may have a reaction where maybe all of them or nearly all of them are being seen to confirm that a chemical reaction has taken place. Like in this one, we are seeing 2 comfortable ones. Another one is there, which is change in temperature, but you will not easily notice it. But the ones you can notice very well is 1, change in state, where you are seeing copper hydroxide, which is a solid, as a precipitate being formed. But number 2, we also look at color change. The color change here is this precipitate that is formed is blue in color. So blue, yes, but these are blue solution and these are blue solid, which is a blue precipitate. You can go further again with this reaction. You can go further with this reaction by using now more of the same ammonium hydroxide, such that you now have your copper hydroxide, which is blue but precipitate, and you add on more of the ammonium hydroxide, which is aqueous, liquid. So we are seeing this one is a solid, blue. This one is a solution, colorless. But this one is being used in excess, a lot of it. What you will see is a change in 1, color, and 2, state. So what will be formed will be a complex ion that is what will be formed. Tetraamine copper 2 ion. We shall also learn this much later in our science lessons, that we shall be talking about how some complex ions are formed. But now here we have a reaction you can easily carry out in your lab. It's not dangerous. And you get shocked. Why is it behaving this way? I've now explained. The solid, which is a precipitate blue copper 2 hydroxide, on reacting with excess ammonium hydroxide, the compound you form or the product you form is a complex ion, which is a tetraamine copper 2 ion. This will also change as much as being an ion is a solution. So what are you seeing? You are seeing change in state from solid to liquid. Solid to liquid. Once you see that, you will comfortably tell whoever has asked that, no, that is a chemical change. It's a chemical reaction. Why are you saying that? It has changed the state from a solid to a liquid, from blue precipitate to a solution. Now, this solution has also a color, and the color is deep blue solution. It forms a deep blue solution. So the solution that is formed is different from this blue. This one is light blue in color, but this one is deep blue in color. And maybe to relate it well, may I use this one and this, because this one is blue and this one is also blue. But where is the difference between these two colors of blue? This one is light blue or pale blue, but this one is deep blue. This one is a solution, this one is also a solution. Pale blue or light blue, deep blue. How did it come about? It came about after copper hydroxide, which is a solid that had been formed here in a process we call precipitation. This is a precipitation reaction or double decomposition. We call it a precipitation reaction or double decomposition. Double decomposition, double means two. Decomposition means breaking. So this one breaks before they form the product. It is not the only product, because the other one will be now ammonia taking the nitrate to form ammonium nitrate. We are not interested in that. My interest was the one that will have changed state. So in the double decomposition, we formed this one as a precipitate. On further reaction of the precipitate with the reagent, it now formed a complex ion, which is tetraamine. Tetra means 4. Mono, di, tri, tetra. Tetra means 4. Mono, di, tri, tetra. You can count up to 10. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So we have 4 of them of what? An amine group, and copper is copper 2. So what are we seeing here? 2 things are being used to show us a chemical reaction has taken place. One is change in state. Change in state to solid, and change in state from solid to liquid. And number 2, we have also seen change in color, where we saw colorless, pale blue, or sometimes just call it blue, giving us a blue precipitate, and this blue precipitate with the colorless solution, more of it, to give us a deep blue solution. Give us a deep blue solution. Now another aspect we can use to show that a chemical reaction has taken place is change, or we can say production of light. Change or production of light. Change of light or production of light. Now in change of light, this one is slightly at a higher level. You remember when we were talking about theories and how certain scientists came up with or developed some of these theories, and how the certain aspects came in when we were talking about the periodic table and how it was developed. And one of the scientists had to look at movement of electrons in an atom. Now, when you are talking about movement of electrons in an atom, meaning that they are moving from one level to another, meaning that from one amount of energy to another amount of energy, as they do so, they release energy. They produce energy. When they produce that energy, they will comfortably show you that a reaction is taking place. Because without that reaction, then movement of those electrons will not take place. So in change of light, it mostly takes place in solid state. In a solid state. A good example here is when you are doing something like a flame test. Flame test. When you get some crystals or a solid, like you can, when you go in the lab, you can do this. You can test sodium chloride as a crystal. You can heat those crystals on a spatula in a flame, in a non-luminous, in a luminous flame, non-luminous flame, which is blue in color. You will find that these crystals will produce a certain color. You can also use it in a solution form. So you can either use it as a solid or a solution in flame test. You will find that it will burn with a golden yellow flame. Golden yellow flame. What does it show? It shows that electrons are moving from the inner energy level, outer energy level to the inner energy level in an atom. What we call sodium spectra. Sodium spectra. Electrons move from the outer energy level or orbital to the inner energy level. Because they have excess energy, they are moving from out, more energy, to the inner, less energy. So the excess energy must be given out. It is given out in the form of yellow color, yellow flame. And that flame is giving out a light. So that light we are seeing is the yellow light. And you will say, oh, that substance that is being tested is a sodium substance. If it is magnesium, you will see a bright white light. You can go in the lab and try to burn magnesium ribbon and see how it burns. When you burn magnesium ribbon, it will burn with a bright white light, just like the one produced when welding is taking place. What does it show? It's still magnesium spectra, just like what we have seen for sodium spectra, and so many others. So by producing light or change in light will easily tell you which kind of reaction is taking place. If it was a mixture of substances, then we can talk about change in light. Maybe it was a golden yellow, now it is shifting to maybe crimson green. You will say that is barium burning. And maybe it changes from crimson green, it goes to red, and you can comfortably now say that is magnesium burning, because you are changing light. That light is a spectra of a particular metal, but production of light is just direct. When you talk about production of light is direct. For example, you know this is magnesium ribbon and I'm now burning it. You don't expect any other light apart from light associated with the magnesium that is being burned, or sodium that is being burned, or calcium that is being burned. But when you talk about change, it means maybe there are a mixture and you sequentially move from one to another because of the different spectra that will be taking place. Now, that is essentially the common aspects you can use to show that a reaction is taking or has taken place. And in all these, we have so many examples we can attach to it. But also remember, we have some reactions that may use two or more of the same. Two or more of the same to show that a reaction is taking place. In whichever case or in whichever way you can be able to identify that a reaction has taken place, always put in mind that safety is important. Whichever way you are doing it, to show that or to confirm that a reaction is taking place, make sure safety plays an important role in those tests. What do I mean by this? We have various reactions that will use any of these to show that a reaction has taken place. But in so doing, a more dangerous or a dangerous thing can be produced, or maybe the reaction is dangerous. A good example in such a state is production of sound. This is a point that you have to note, production of sound. You remember I mentioned a bomb. We have various reactions in the lab that can easily produce sound to confirm to you that surely a reaction has taken place. You have to be careful with such, because in producing that sound, it may cause breakage of apparatus and you may not be safe. In addition, most of the reactions that produce sound, most of the reactions, not all, but most of the reactions that produce sound also produce heat energy. So by producing that sound, in addition to producing high amount of energy, if you are not so careful, you may get burned. Maybe choosing a good example to use here is when you are diluting water in sulfuric 6 acid. When you have a lot of sulfuric 6 acid in a container and you add in a lot of water, that is very dangerous, because the high temperature that will be produced and also the reaction involved in water getting dissolved in the acid being so vigorous, some of the acid will splash out. And when it splashes out, it will be splashing on you. And it will also produce a sound. It will also produce a sound because of the high intensity of heat energy being produced at one particular point of water being in touch with the acid. So it can easily burn you. Another thing here is production of sound involving production of a gas. Production of sound involving production of a gas. And this one will be taking me to another aspect that I wanted to mention as I relate it to production of sound, and that is production of scent, smell. So we have production of either we can call it smell or scent. Smell or scent. Now this one is associated with the sound, because you will find that some of the reactions where a gas is produced can involve production of sound, but not in all cases. There are cases where the reaction may not produce sound, but a gas will be produced. That gas can easily be colorless, so you may not see the gas, but it may be producing a certain kind of smell. So by you observing, getting the smell using your nose, we can say observation of smell. So when you observe that smell, then it will have told you that a reaction has surely taken place. A good example is when you are producing ammonia. You are producing ammonia, you are doing a chemical reaction in the lab to produce ammonia. Ammonia gas is colorless. How would you tell that ammonia gas has been produced? By you getting it with your nose. However, as I'm explaining dangers, when you are producing gases, don't ever smell in a container directly, because some of the gases are poisonous, they are irritating, they are acidic, they are basic. So when you smell directly, you will get too much of it into your breathing system and can easily collapse your lungs. Like ammonia is a basic gas, so you don't breathe a lot of it into. So the best way to notice whether there's a change or not, you swallow the air, whirling the air to your side, so that you only get a tip of it. Once you get it, in terms of the smell or the scent, you will have known that surely something has been produced. Now, smell is mostly associated with the gases, and scent is associated with the other products that can be formed. For example, sweet smelling products. We don't call them sweet. So that's why you say now a sweet scent is produced. A good scent, not sweet, but a good scent is produced, because sweet means you have used your tongue to taste, which you cannot be using. So you are using your nose. So we say a good scent is produced. A good example here is when you are in an organic class, organic chemistry class, and you are producing a perfume, what we call an ester. An ester is just a perfume. Ester, that is a perfume. Esters are just perfumes. Perfume is a commercial name, but the chemical name is an ester. So how do you get that? You just whirl and oh, this is nice. So I have produced a good perfume. Even if it is good, don't smell it directly. But smelling is mostly associated with the gases. For example, I've just talked about ammonia. You can talk about nitrogen 4 oxide. You can talk of carbon 4 oxide and so on. But now remember, not all gases will produce a smell. Like carbon dioxide, it will not produce a smell. So on that one, you can just use production of sound, that is effervescence. So you will see that in all cases, make sure that you see how either of these is attached or associated with you being able to identify that reaction as a chemical reaction, or that reaction as not having taken place, by using all of this, because one case cannot be enough to identify a particular chemical reaction. Now, I gave you a statement in our previous class of classifying your sweating after maybe doing some work. as either a chemical change or a physical change. May I now take this opportunity as we complete our lesson today to identify that as a chemical change or a physical change, and in association with what we have just learned. When you are sweating, it means there are two serious things that are happening in your body. One, your liver is doing a lot of work, converting the stored glucose into that form that can be utilized by your body to produce energy. That process produces a lot of heat energy, which must be removed from your body, and it is normally removed through your skin, and that's how you get to sweat. Another thing that is happening is your muscles will be doing a lot of contraction and relaxation and all manner of work that is associated with what you are doing, and in so doing they also produce a lot of heat energy, which is produced through your skin in the form of sweating. And sweating means water is being removed in your body, and as it goes out with that heat energy, what we call in science chemistry part as latent heat of vaporization. When that water evaporates from your body as sweat, it goes away with that heat energy so that it leaves your body skin cold, what we call regulation of temperature. So what is it? Is it a chemical change or a physical change in your body? That is a chemical change. It is a chemical change. And how do you know that that chemical change has taken place? We go to change in temperature. You see that your body is changing in temperature, and comfortably now you can see, oh, this is a chemical change that took place inside my body, chemical change. But whatever is happening on the surface of the body is a physical process. It's just a physical process of evaporation. The water evaporates as sweat, evaporates, that sweat is evaporating. As it evaporates, it goes away with the heat energy, leaving your skin cold. That is a physical process. But whatever is happening inside is chemical, and that is where the change in temperature is taking place. So the change in temperature is the one now we are using to show us that surely your muscles are working and your liver is also working. That marks the end of our lesson today. Thank you.